First of all, thank you all for being here. It's my pleasure to give this talk. And in this talk, I'm going to tell you guys how to use an ensemble learning approach to predict a rare event. And in this case, the rare event we're trying to predict is when an internet user makes a purchase online. So first, I'm going to tell you what the business context is, so you would understand the problem we're trying to solve. And then I'm going to tell you about ensemble learning, in particular stacking, and how it works in general. Then finally, I'm going to tell you guys about how we implement and deploy the models in production. So first of all, what is the problem we're trying to solve? Well, Velocis Digital is a digital advertisement company. So here is a web page. You can see there are a couple ads online. First of all, on the top of the page, you see like a Toy Story 4 ad. At the bottom, you can see a couple ads for headphones. So how does it work in general? Well, it all starts when the user browses a website. When the signal of a user browsing website gets received by an ad exchange, the ad exchange sends that signal to us. Velocis Digital receives about 100 billion requests on a daily basis. And then we're going to look at the user and then the website that they're browsing, and we're going to make a decision whether we want to serve a user an ad. If we decide we want to serve the user an ad, then we're going to participate in something called a real-time bidding process. It usually happens really fast. We typically have a response time of about 10 milliseconds. And if we win the auction, then we're going to serve the user an ad. And in the meantime, if we don't already have a cookie on the user, then we're going to drop a cookie on the user. And once the cookie is dropped, we're able to use the cookie to track some user activities. For example, when they browse certain ad-supported website, we're able to collect that data. In our system, there are about 1 billion users for which we have those data for. And if in the future, the user makes a purchase on one of a client's website, then we can actually collect that signal via something called a pixel that will be placed on the client's website. So just to summarize, we run campaign for our clients, usually could be thought as brands or ad agencies, and the client usually has some sort of KPI they're trying to drive. For example, they may want to increase the purchase rate of their products. And we would receive credits if we served an ad to a user and the later user made a purchase. So we basically want to serve ads to people who are more likely to make a purchase in the future, or more generally want to serve ads to people who is going to perform an action that's desired by our client. And we call that action a conversion. So the question is, given the data we have about our internet users, how to predict the likelihood of them converting? So you can imagine we have all these different types of data about a user, and we want to predict whether the user will make a purchase in the future or not. But we also want to have some additional requirements. The first one is we want to allow multiple contributors over time. The reason being that we have a team of data scientists and engineers contributing, working on the model, constantly working to improve it. We want to be able to work in parallel and concurrently and somewhat independently so that one person's contribution doesn't break the model that's already in production, but also multiple people could also contribute at the same time. And we also want the effort we put into making the model into production to be generalizable to other use cases. We don't want to just build a one-off solution because it takes a lot of engineering resources to build a model deployment pipeline. So with that in mind, the solution we choose is to use ensemble learning. So what exactly is ensemble learning? Well, it's really just the effort to combine the predictive power of multiple learners to obtain better predictions than with just one learner alone. So with ensemble learning, we're going to combine multiple models to give a single prediction, and that's going to increase the diversity of the models and algorithms used, which has been shown to be crucial in improving the predictive power of the model. So what are some examples of ensemble learning? Well, the most common one is, we would see, it's called bagging. Well, bagging is short for bootstrap aggregation. We could imagine, say, if you want to train a decision tree classifier, and you realize the model has overfitted, And what you can do is really just to train the decision tree classifier on the subset, train many decision tree classifiers, each on the subset of the training data, and possibly each on the random subset of the features as well. Then when the time of prediction comes, you're going to just take votes from each of the individual decision trees. And with that, we would get something called a random forest. The key point of bagging is the individual learners are trained in parallel, and at the time of predicting, all of the individual trained models are going to vote on the outcome. Another example of ensemble learning, Another example of ensemble learning is called boosting. So when we use boosting, individual-based learners are trained sequentially instead of in parallel. The way boosting works is samples that were misclassified by the previous learner will receive more weight in subsequent learners. Again, let's take decision tree, for example. We train decision tree on subset of the data and predict on the whole data set. We realize there are some data points that were misclassified. And in the next iteration of training the model, those misclassified samples are going to receive more weight. And in the meantime, we're going to use the accuracy of the trained model to assign weights to all these models. We're going to iterate the process until we're no longer seeing improvement in our error function, where we have reached the maximal number of iterations. There are different ways of doing boosting. One example is called adaptive boosting, which basically just does what I described. It assigns more weight to misclassified samples. There is something called a gradient boosting as well, where instead of fitting models try to predict the actual class of the data points, it's actually trying to fit to predict the residual error of the previous model. So it's basically some form of performing gradient boosting on the loss function, hence the name. It's basically performing gradient descent on the loss function, hence the name gradient boosting. Then there's also the model XGBoost, which is basically a full-featured, efficient implementation of gradient-boosted trees. It supports fast learning through distributed and randomized computing, and it uses approximation algorithms to find the best tree split when we are choosing features. So these 2 points offer huge improvement in speed over, say, like the scikit-learn's naive implementation of gradient-boosted trees. And also supports regularization and tree pruning, and can intelligently and efficiently handle missing values. So this model has really gained popularity. Basically, every winning kernel in Kaggle competitions, you would be able to see this model. So those are some examples of ensemble learning. There is another one called stacking, which is the one we choose to use in our problem. So what is stacking? Well, as I mentioned, it's another ensemble model where it has a layered structure. So you can imagine we have these different layers, and in different layers we have different models. Predictions from models in one layer is going to be input into the models in the next layer. You could imagine we could have multiple layers of these models, but eventually we could only have one single output. Maybe it's more clear to just look at the picture where we're going to have 2 layers of models. The first one has 4 base learners. It takes the data and produces 4 outputs. And those 4 outputs get into the second layer, where each has only 1 learner. And that learner produces a final prediction. So what are some benefits of stacking? Well, since we have individual base models, stacking could increase the diversity of the algorithms and models used. And instead of having a winner-takes-all approach, which we would do when we only have 1 model, stacking allows us to combine different data sets. It also enables the parallel development scenario that I described. So each individual could just develop a base model. Later, the base model would just get into the stacker to be stacked. So the individual base models don't have to interfere with each other. Since we're using individual base models, we can also capture the different categories of features used. If we were to combine those features into one single model, that could result in very high dimensionality, and that gets computationally expensive very fast. So here's an example of how having a stacked model might work. Let's say we have 2 layers. The first layer has 3 base models. we may have XGBoost classifier that predicts the probability of a user converting based on his or her browsing history. We could have a random forest classifier that predicts conversion based on the user's response to previous ads. For example, whether the user clicked on the ads or not. We could have a logistic regression that predicts whether the user is going to make a purchase based on a user's activity level, like how long the user has been active, et cetera. And with the 3 predictions, that's going to be the input to another XGBoost classifier that's going to predict the probability of conversion based on those inputs to produce a final probability on conversion. So now that we know what the architecture looks like, what are some ways to optimize the model? Basically, we have this train, validate, and test machine learning pipeline. So how does that apply in the case of a stacked model? Well, just with every model, it needs to be selected or needs to be tuned for hyperparameters. For example, we could use some form of randomized search in the hyperparameter space, and we use k-fold cross-validation for that. One thing to pay attention to is, in the case of stacked model, we don't want the base model and the stacker to be trained on the same data. So we're going to first tune the base model using k-fold cross-validation to select some set of hyperparameters. And then we're going to fit the base model on the train fold and predict on the test fold. And the predictions on each of the test fold would be the new folds for the stacker. And then we're going to recreate the train and test fold for the stacker using those new folds. Well, the reason we don't want them to be trained on the same, we don't want the base model and the stacker to be trained on the same data is because we don't want the stacker to improve in-sample estimation accuracy. We want the stacker to improve out-of-sample prediction accuracy. Hence, we need to do some shuffling of the training data so the stacker is trained on different training data. There are also some things we need to pay attention to when we use a stacked model approach. Due to the sequential nature of stacking models, it could lead to overfit. So we want to take some precautions against it. For example, we first want to make sure there's enough data to support stacking. We don't want to train a complex multi-layer stacked model when we only have like 3 data points. We also want to use some form of regularization. For example, we could use the early stopping technique, or in the base models, there are usually some complexity-related hyperparameters. We may want to put a cap on those. Another thing that's kind of special to stacked model is we want to make sure that the base models are mutually orthogonal. So here's what I mean by having mutually orthogonal base models. We basically want the predictions produced by the base models to have low correlation. If they were to have high correlation, it means we're basically sending repeated information into the stacker. That could lead to overfit. So when the base models have low correlation, it's intuitively that's just saying all the base models are skillful, but in different ways, and it's really the stacker's job to pick which ones he wants to use. So now, given that, we need to think about what type of evaluation metrics we want to use to really evaluate the performance of the model. Well, there are so many metrics we could choose from. It should really be depending on what the problem is. So let's just first briefly revisit what the problem is. So remember, for each ad campaign we're running, there is a ranked list of users that we want to serve the ads to. And we call this ranked list of users an audience for that campaign. So now that we have this predictive model that produces probability of a user making a purchase in the future. So that's a natural ranking of the users. And for each audience, we have 2 goals. The first one is really just to put as many future converters in the audience as possible. So the ads would be served to people who are more likely to make a purchase. And also, a second goal we have is to rank the future converters higher than non-converters, so that future converters would be served first. Also, they would be priced higher in this case. And based on the goals, which shows our evaluation metrics to be, the first one is recall, which is just to make sure we include as many future converters as possible in our audiences. The second one is NDCG. So what is NDCG? Well, it's short for normalized discounted cumulative gain. Basically, it's an evaluation metric that's somewhat popular in information theory, which is usually used to evaluate the quality of ranked list of documents. What it's trying to capture is the quality of the ranked list should be dependent on where we put relevant items and irrelevant items. So we want to put relevant items at the top and irrelevant ones at the bottom. So cumulative gain just means we get points for putting each relevant item in the list. So cumulative gain can be thought of the total utility provided by this ranked list. And discounted means we want to penalizing for putting relevant items lower in the list. So we're going to penalizing discounting by the position of relevant items in the list. And if we just use discounted cumulative gain, we cannot compare items or rather lists of different length because you can imagine it's easier for a longer list to have more relevant items. So we want to have some form of normalization. Well, the form of normalization we use is basically we're going to divide by the discounted cumulative gain of a perfect ranking. By a perfect ranking, I just mean a list where all the relevant items are at the top of the list. So after normalization, NDCG is going to be a metric between 0 and 1. Here is the math of how to calculate that. What you really need is just to come up with a number that stands for relevance in this case. And I'm also including an example of how to do that if you want to study how it actually works. So that's basically the summary of how to solve that problem, at least from a theoretical aspect. So now, how we actually implement and deploy the model in production. Well, here are things we want to consider before we actually build the model deployment pipeline. First, it has to be scalable. So in our system, we are fitting hundreds of models daily, and each of these models needs to be scored on 1 billion users in our system. So whatever implementation we choose has to be able to support that. The second one is we want the process or the pipeline to be user-friendly. By users here, I really mean just our data scientists who like to develop models in Python. So we should be able to support that as well. The third one is, again, we want it to be generalizable. So the process should be generalizable to other model fitting and deployment use cases, so we don't just waste our engineering resources for a one-off case. And our solution for that is a Hunch, which is an in-house library that allows the functionality of Python but the speed of Scala. What Hunch does is it supports serialization of scikit-learn models and XGBoost models into Hunch representations. And it also supports deserialization of Hunch representations into Scala functions. So the way it works is, in the model fitting stage, the model is going to be fitted in its native language. In this case, it's going to be Python. And it's going to be fitted on a smaller scale on roughly 200K users for each model. And the fitted model is going to be serialized into Hunch JSON objects. And when the time of scoring comes, those Hunch JSON objects are going to be deserialized into Scala functions. That's going to take a vector. That's going to be a feature vector, and it's going to spit out a class-like probability. When we're scoring, as I mentioned, and we're scoring on 1 billion users in our system for each model. And here are some stats on the performance of the library. So we run about 600 models daily to predict our 1 billion users. And each user is a row of feature vector of 7K plus entries. And we make an estimated number of 200 billion row evaluations in that job. And the models are running batch. By the models, I mean the scoring job, the job of scoring users. So that's going to be running batch, and it takes about 5.5 hours serially, and that comes to 5,300 hours of virtual core time in Spark. So I don't have data on how long it would take if we were to do everything in Python, but I can tell you it wouldn't be realistic to support the job to be run daily. So the Hunch library we built has provided huge improvements in speed over just using Python models to do the scoring. And I think that's it. So in this talk, I basically told you guys the business problem we're trying to solve, and theoretically and from a modeling perspective, how we would solve it. And I also told you guys a bit about how to do it in practice, how to support such a complicated and expensive system in production. Hopefully, you were able to take something away from the talk and apply it to our own problem. And thank you.
We have time for questions.
Thanks for the talk, really enjoyed it. So anytime I've been browsing for something on the web, and then I end up purchasing it through a link, like an ad. So I've already bought the item, and then I'll be browsing another website like a week later, and that advertisement for that item will show up again. Somebody's serving me the ad, they think I'm going to buy it again. So how does your modeling process take that into account?
So for example, as we mentioned, like one example of something we could account for in the models is whether the user has made a purchase or not. There are some products that make sense for people to purchase over and over again. For example, if you order pizza on the internet, and we think it's possible that this person is going to order again sometime in the future. So we might just try to serve you an ad over and over again, versus if you're maybe just bought a car on the internet, and we're like, this person, I don't think he's going to buy a car again in 6 months. So we're not going to try to serve auto campaigns to you over and over again. So it really depends on the product and the client we're working with.
So in the schedule title, this talk was described as having to do with rare events. You didn't really discuss how the scarcity of the events figures into your approach. Could you maybe comment on that?
Yeah, I guess for rare events, the reason, so first of all, we need to acknowledge the fact that a user making a purchase on the internet is indeed a rare event. It doesn't happen very often. The way we use the rare event is really where what we call converters in our training data set are oversampled, and the people who are non-converters are undersampled. So what we're doing is really trying to balance the data set.
Hi, you were talking about ensuring that your learners do not converge on orthogonal features. So I was just wondering, what measures do you take to prevent that from happening?
So we usually just look at the correlation matrix of the predictions produced by the base models. If there are two models who have high correlation, for example, if the correlation is above 0.75, then I'm going to drop one of the base models. And we're going to deem the base model not providing additional value into the stacker.
These models are likely, I guess, to have different levels of performance across. And so I was wondering if in your stack model, are you going to, you just like in the second layer is actually just learning weights of the first base model to determine which one gives the best results? Or are you actually relearning and relearning and then relearning and then relearning, so on?
Yeah, so the base models are tuned first, and then the stacker is tuned on top of that, and then we refit the whole model after the tuning is done. But the reason we wanted to use the stacker, or the general philosophy about the stacker, is we have individual base models of different performances, and it's really the stacker should be intelligent enough to pick up which one's useful, and it's going to put more weight on the models it thinks is useful.
Yeah, you mentioned about the model fitting for multiple users, and then there is a hunch function that converts into the scalar function. So could you explain on that, like what it does to convert from Python to like Scala?
Yeah, so the Hunch is just a library we built. It's very similar. You may have heard of something called predictive model markup language, where the fitting of the model is done in one language, but the actual prediction is done in another language. So we basically just turn fitted model into, that's fitted in Python, turn that fitted model, which is a bunch of coefficients, right? Turn that into a JSON object in the Hunch library, using the Hunch library, and then we're gonna, when the time comes for us to score on 1 billion users, we're just gonna take that JSON object, turn into a Scala UDF that basically just takes a feature vector, which is a bunch of numbers, and spit out a probability. So doing scoring in Scala gives us huge improvement in speed.
Sure, and all these data are in the Hadoop or cloud? I mean, how is your data stored? Like,
Sorry,
I mean, the data, 1 billion users and all those data, how it is stored? Like, are you in Hadoop or cloud, AWS?
No, we have our own in-house clusters for data storage.
Okay, thank you.
If there are no further questions, let's thank Susan again.